Okay, I'll kick us off here. All right, welcome everybody to the first seminar in our series for research cyber infrastructure at the University of Hawaii. I'm honored to welcome Dr. Henri Cassanova, professor in information and computer science at the University of Hawaii Manoa. He received his doctorate in computer science from the University of Tennessee, Knoxville in 1998 and has had a career spanning almost 3 decades, with two of those nearly at the University of Hawaii. He's internationally recognized for his contributions in the area of high performance computing, with a particular focus in scheduling and simulation of parallel and distributed applications. He is a co-creator of the SimGrid and Wrench frameworks that lower barriers for entry for simulation-driven research and education. His work is supported by numerous NSF awards and has led over 100 peer-reviewed publications. We're very lucky to have him today to share his insights and his latest work on using cyber infrastructure resources to improve the simulation of cyber infrastructure resources. So, all right, take it away, Henry.
All right, thank you. Well, so this seminar is about people talking about how they use the resources provided by ICS for cyber infrastructure. And so I'm going to tell you what we do in ICS. If I can go to the next slide. So the research is ongoing in the ICS, Information and Computer Sciences Department at Mānoa. And the work I'm going to talk about today is myself at the PI and then two graduate students, Jesse McDonald, who's graduating, we think, in May 2026. Sorry, first typo of the slide, with PhD. And Jeff Wong, I'm off by 1 year. What happened? Graduating December 2025, so in a few months. And this work is supported by two of my NSF grants. So here's the big picture. There's a lot of CS research that seeks to improve the state of the cyber infrastructure. Right? So I'm not a cyber infrastructure user, like would be a physicist or a biologist, but more like a cyber infrastructure researcher or developer. And that research relies on experiments where you run those biology, physics applications on hardware resources and observe and try to improve how they work. And it turns out that conducting these experiments is surprisingly difficult. And so a lot of the work I've been doing over the last decade has been to explore an alternative, which is simulate the execution as opposed to running them for real. And the challenge is, so somehow that's challenging as well, but the challenge is how do we make those simulations happen? So you have a real cyber infrastructure, and here now I have a software artifact that simulates it, and how do we know it mimics the behavior of the real system we're using? And so a lot of my group's research is about developing solutions for this challenge. And to do this research, we happen to use the cyber infrastructure itself, and in particular, the POA cluster at Mānoa. So a lot of the research in the cyber infrastructure field is about the performance behavior of systems and applications, right? A lot of our work is about performance, and there are many research questions or engineering questions, such as, and not limited to those, which hardware configuration is best for a particular application, how should you structure and implement the applications? What are good running models? What are good runtime system designs? What resource management and scheduling algorithms should be developed, and so on. So every year at the conferences in the field, there are dozens and dozens of papers who explore those questions. And here I use the term performance in a broad sense. Could be, of course, response time, power consumption, reliability, and whatever is of interest. And so there's some theory in there, and you can be a theoretical high-performance computing researcher looking at the cyber infrastructure, but most research is not theoretical and relies on experiments to validate research results. That's because the theory is fascinating, but to be tractable, you need to make simplifying assumptions, and then often your results don't directly apply to practice. So what I mean by an experiment is take a scientific application of whatever field of interest, secure access to some cyber infrastructure resource, and then run the application possibly many times, and then observe. And maybe run it in a different way, observe and complete which way is better. Okay? And so that seems beyond easy, because it should be pick a bunch of applications or configurations, get access to some system, run everything, analyze the result, and then either if you're an engineer, pick whatever approach you want, if you're a researcher, write your paper. That sounds great. But sadly, there are many difficulties in a way that kind of boggles the mind, actually. So those experiments are hard. First, well, they are labor intensive. And if you've done any of those, you know how much time this takes. You need to install and configure software. And containers have made this better, but somehow my graduate students and all graduate students, as I can tell, in the HPC group spend a lot of time configuring and installing the software, and you need to acquire the resources. And then the runs are long because we do HPC for long-running applications, so they consume time and energy. So a lot of CO2 footprint. There is a great PhD dissertation from 3 years ago where the last chapter in the student writing, here is the carbon footprint of my PhD dissertation. I should never have done it. I'm thinking of quitting this field for that reason, right? So this is quite a shock when you read that dissertation, when you get to the end. The main research impediment is they are limited in scope. So let's say I'm at UH, I'm a researcher, I have access to COA. I run everything on COA. And then I publish, and then reviewers will say, well, yeah, COA has that network, what about this network? COA is this big, how about that big? COA has those kind of GPUs, what about those GPUs? And therefore, we don't know if your resource can generalize. So if you have contacts in the field, then you have a count on multiple COAs, which is what I do, and then you can say, okay, we'll run on 6 machines, but not everyone has access to that. Excuse me. Also, the execution is not perfectly observable. Logging has high overhead. So we need to log the execution to get a trace of what happened. And if you log everything, well, that actually slows everything down, and not everything is loggable. For instance, you want to say, hey, on that network link of the network topology, what was happening at time t? Well, we don't necessarily have that information available. Of course, the killer is non-perfectly reproducible and sometimes downward read results. This is something that people outside the field typically don't expect because we're looking at human-made systems, so this just should be fully deterministic, and we build them after all. As opposed to, I don't know, a physicist looking at galaxies. Well, okay, we expect noise and weirdness, but maybe not in a computer. Here's a dissertation by Tom Cornebys, which is outstanding, called High Performance Computing Toward Better Performance Prediction and Experiments. And he did many things in there. And I was on the committee, which is why I was very aware of that work, but he had access to, I forget now, I'm going to say 10 different clusters in Europe. And he ran those benchmarks, doesn't matter if you don't know what they are, MPI, DGEM, HPL, on those clusters, I think every day for years. He started from the beginning of his PhD and then kept them running, which is a huge amount of data about what happens if you run benchmarks continuously. And chapter 10 and 11 are all about weirdness. And that's actually a required reading in my graduate level class. So I can't possibly show everything in there. And it will be probably way more entertaining for me to talk about that work for an hour than what I do, because that work is absolutely horrendous. But it's the kind of thing that he was able to show. And again, it doesn't really matter what anything is. Those graphs on the left, right here, high means high performance, low means low performance. And on the x-axis, it's the time. And you can see that, well, it jumps up and down. And it's because of all kinds of things, hardware upgrades, downtime, software misconfigurations, all kinds of things that he has tracked down over the years. And he found 7 completely unexplained problems. All of them, he thinks, due to temperature. One of the explained ones is unbelievable. It's on Wednesday in a French city, Wednesday afternoon, the benchmarks all slow down all the time. That's because on Wednesday afternoon, French kids in junior high don't have class. And the city organizes school of their assembly. And so you have 80 warm bodies standing always in the same spot by the same cabinet for half an hour when they're being told about high-performance computing. The temperature rises 2 Celsius. The microprocessors downclock 0.1 gigahertz. And it's a distributed application. And so now there's load imbalance, and now everything slows down. It took him, I think, 8 months before figuring this out. And so when physicists say, oh, you guys have it easy, computers are easy to understand, well, I mean, it's not that simple. So if you're a physicist, you don't care about this, right? You care about your output. Well, maybe it took longer. So if it really slows down like crazy, maybe that's not right. But if you're a cyber infrastructure researcher, well, then it's problematic because then your experiments mean nothing. They're so noisy. And so in a field in which experiments are difficult, what you do when you do simulation. So for instance, if you do computational fluid dynamics to study airplanes, you don't fly a bunch of airplanes with sensors and crash them to see what happens. You do computational fluid dynamics. And so if you plan cities, you don't build a bunch of highways to see what happens. Instead, you just simulate traffic. And so we can do that as well as computer science researchers. And so the advantages are many. Of course, it's less labor intensive typically to develop a simulator than the real system. takes much less time and energy, less energy in general. Everything I'm saying here, there are cases where it's not true, but in general, much wider scope. That's what people love. Say now I can make up whatever scenario and publish my paper saying what you wanted to try a cluster with 1 million nodes and a crazy network. Well, there it is, because I can just simulate it. It's perfectly observable because we can log everything because it's all software now, and perfectly reproducible. And if you want to simulate weirdness, you can, but you can do it in a deterministic fashion with seeded random number generator. So basically, addresses all the issues that researchers have had with experiments for years. The big question is now we have implemented a simulator. It's a software artifact that limits the performance of COA, let's say, and now we never use COA again. The question is how accurate is it? Right? And of course, it cannot be perfectly accurate. How big are the discrepancies between the real execution and the simulated one? And if it's not accurate, it's not useful. And there are a lot of inaccurate simulators out there in the field used for research, which is a huge problem. In some fields, that's no longer an issue. Computational fluid dynamics, most people really believe that those numerical methods give you the right answer within some decision, and it's used all the time. But what about simulation of cyber infrastructure systems? Okay, so that was the context. Stop me if you have any questions that I go, of course. And so I'm going to talk about that question of simulating the cyber infrastructure. And then one thing we're doing in our lab, which is automated simulation and calibration. Okay, so we want to simulate platforms on which we have runtime systems to execute applications, which is exactly what's happening on COA every single day. We want to study those human-made computer systems that are in principle discrete and deterministic, so it should be easy. So building an accurate simulator, if you start without ever working in this field, should be compute the times at which different execution events happen, like a job start, a file transfer completes, and then that's your simulation. It's a timeline of what happens throughout the execution. So here's an example. One area of research that's very popular is batch scheduling simulation. You may not think so because all the clusters out there basically run Slurm, and Slurm hasn't changed that much. But every month, there are papers being published about yet a new batch scheduling algorithm, a new batch scheduling system. What do these people do? Well, they care about, let's say, job completion. So let's say we have a very naive view of the system. We care about when jobs complete, and we have perfect data about what jobs want and what they actually do, requested and actual job time. So you know what a batch scheduler is? It's very simple. On the left here, we've got a schematic description. You have a set of compute nodes and a batch queue, which is a queue of jobs waiting in line to run. And there's an algorithm that decides who gets to run when. And the job says, I want some number of compute nodes for some amount of time. Right? So there are many run-on algorithms. There's an entire conference dedicated to that topic alone. I want to simulate what's called, some people call a backfilling algorithm, which is what Slurm does on COA. So for instance, right now, on the system, the purple and the green jobs are running. On the right side, we have got a Gantt chart, the time on the horizontal axis. And the pink and blue jobs are stuck waiting in line. And then at some point, the green job terminates earlier than planned, which happens all the time. And now, right now, we can now start the pink job that has been promoted to run it a bit earlier. Okay. So that's a very broad view, but it doesn't really matter what we're doing, I think. Even if you don't know anything about batch scheduling, it's all going to make sense. And so now, basically, what I showed here is that we can draw by hand this entire thing. It's just really tedious to draw if we have a lot of jobs. But we can draw this Gantt chart. At time 10, the green job finishes. Therefore, the pink job gets to start now. Therefore, the blue job will now start earlier. And now we go to the next time step and we keep going. So very easy. We call that a simulator, and I have it in quote here because it's basically a piece of code that computes job start times and completion times. And then based on that, you can see whether that algorithm is better than some other algorithm. And so it seems that cyber infrastructure simulation is easy if that's what you want to do. But if you look at the literature in batch scheduling, the previous simulator is too naive. I mean, it's not too naive, it's 30 years old. 30 years ago, papers had exactly that picture in mind. But now we know more things, and so we have to simulate more stuff. For instance, jobs perform I/O. The jobs use the network. Some jobs can share a node, and then they may share the memory hierarchy. So the system is not as simple as just drawing rectangles on a whiteboard at the right times. But then what one would think, well, you have just more events. Now it's not a job start, maybe it's a clock cycle completion, it's a disk block transfer, it's a network packet arrival. So it's the same stuff. The system is now more complicated, where now it's not just a whiteboard on which I draw rectangles, it's 16 compute nodes, 4 routers, 4 switches, 1 disk, and every compute node has maybe 4 cores with shared L2 cache and a big shared L1 cache reports on board and so on. So now it's more for a real system. And now, well, my simulation will look like this. It's the same thing. I just have tiny little rectangles that symbolize tiny little activities. So every little network rectangle is an individual network packet as opposed to an entire network transfer. An entire job execution now is a bunch of sub-activities. And you see that at some time, the pink job is the green job finishes and the pink job starts. And now it's just about simulating all kinds of microscopic events as opposed to macroscopic events. Okay, so now we have to do this. And so can we do this? Well, people have done that. And for instance, there are simulators, so-called cycle-level simulators or cycle-accurate simulators. Gen 5 is very well known for CPUs. GPGPU sim that will say, give me the specification of your microprocessor, tell me the assembly code and the binary code you're running on it, and then I'll simulate all the little activities at each clock cycle, and then I tell you that code will run in 72 seconds. For networks, if you're a network researcher, the one you use is NS3. It's a packet level simulator that simulates the entire TCP stack, for instance, and individual packets on routers. So again, it will tell you, oh, you're sending 2 gigs from here to there. I do all the packets. That will take 13.1 seconds. And for disks, there's a very old one that keeps being updated from disk sim. And there's a new one called SSD sim. Same thing, where you say, I want to load a JPEG of 2 gigs. Well, it will tell you, okay, that's actually a million little disk blocks, and here's the sequence of events, and turns out that will take 3 seconds. And so people have developed low-level simulators to do all this. And so one idea is, well, right, let's just do this then. And then they will generate for us that beautiful Gantt chart with a million little rectangles. But then at the end, we see what happens, and we can extract the information we need from that, for instance, at which time each job completes. So conceptually, it's trivial. But we hit a practical barrier in that now the number of simulated events is linear in the simulated compute data volume. If you take an algorithm class, you think linear complexity is great. Yeah, I mean, it's better than quadratic. But simulating a 10 gig data transfer is 10,000 slower than simulating a 1 meg data transfer. As a result, simulation times can be orders of magnitude longer than simulated times. If I want to simulate what happens on TOA for a week, maybe I need to run on TOA for a year. That is a showstopper for simulating anything large. So if you're a network researcher working on network protocols, if you're a computer architect working on Ucache hierarchy, that's okay. You simulate 2 seconds of computation or data transfers, and then you draw conclusions. If you do research in cyber infrastructure, you have to simulate things that will take a week to run, and so now that takes 10 years. And so we can do this. So we must make the simulation scalable so that we can simulate the execution of large stuff without spending too much time doing it. And so we have to give up on that beautiful picture I showed with all the little rectangles. We have to give up on simulating low-level events. We must design mathematical models that capture the macroscopic behavior that arises from microscopic events. And of course, domain scientists do this all the time. If you do biology, you don't go all the way back down to molecular level, right? Or if you study gases, you do, as a physicist, you do partial differential equations, you don't look at particles. And so here we need to do the same thing. And they should scale, meaning ideally, a 10 gig data transfer can be simulated as fast as a 1 meg data transfer. And so we want to go from that picture on the left, where we give the simulator 4 hardware specs, software binaries, and we do microscopic simulation. And it's amazingly accurate, but it takes a million years. And we want to go from that discrete thing, which we wish we could do, to a continuous approximation of it, where we give a microscopic simulator some vague parameters that describe what we think the underlying behavior is. And now we get that picture on the right, and hopefully it's a sufficiently close continuous approximation of the full and discrete picture on the left that we can still draw meaningful conclusions. And so decades of research up to now have produced such models, and they can be very accurate, provided the parameters that define their behavior are correctly shown. And that's really the common thing. So myself and others over the last 2 decades have come up with simulation framework. At the beginning, the SimGrid one was mentioned, for instance, where we did what I just said, where we said, okay, what is a good mathematical model that is tractable, that is fast, and that will be somewhat accurate? And we got surprisingly good results. For instance, for networks, we got a really milestone paper that said, look, you can simulate networks 1,000 times faster by using only a few percent accuracy. So that sounds really good. The problem is those mathematical models now, they have parameters to guide their behavior. And the challenge is, what does the user do? How do you say what the parameters are? The good values are unknown, possibly very complex functions of hardware specifications. So I go back 1 second. On the left side here, we can't use it because it's too slow, but the good thing is the parameters are just the full specification of the hardware and the software, and so we have that. On the right, we have high-level parameters that may be a little bit magical. And so the problem now is, well, great, you guys have published a bunch of papers showing that your models can be accurate, but now for my stuff, how do I pick those parameter values? And so we need to calibrate parameter values based on available ground truth data, like any good scientist should do. And so I'm going to talk about what we've been in my group with those 2 students, Jesse and Jeff, over the last couple of years. So the need to calibrate simulation parameters is obvious. If you talk to any domain scientist, physics, for instance, you tell them, yeah, you built a simulator of your thing, and now you have ground truth observation data, and I need to make your simulator fit the data by picking the parameters. And every physicist wants to want, of course, I mean, we're doing science, aren't we? So yes, you need to calibrate your simulator. That's the first thing you do when you have a simulator. And a lot of people publish results in Cyberinfrastructure, HPC, distributed computing in simulation because of all the advantages I've mentioned. And we try to say, what is the state of the art? What do people do to calibrate? So that's what we'll be on the other side of the fence. We've been, here is a simulation framework. Go use it. It has a bunch of great models. By the way, that one takes 3 parameters, alpha, beta, gamma, delta. And if you pick good values, it's going to fit your system with them. So we looked at 114 papers published over a 5-year period that includes results obtained with the popular Cyberinfrastructure simulation framework, the one that I actually created 25 years ago, and that has been taken up by all my former postdocs and PhD students, the SimGrid. And why did I pick that one? Because I think it's great, of course, because I did it, but it's because it's the only one that keeps track of the papers that actually use it, not just cite it. So we have a whole database of papers that said, we use SimGrid to implement a simulator, and here are the results it gave us. So now we can go back and look at what's happening. And it's super scary. So we look at those papers, and we find that 85 of them include only simulation results. So they basically downloaded SimGrid, said, now implement a simulator of freedom, meaning all the parameter values are default, meaning they are simulating something, a system that could exist, but that doesn't map to any real system we have access to. In some of those papers, I can see what they're doing this, and it's actually not so bad, and they simulate 1 million different systems, and the results are good across 1 million, so like, okay, well, it's probably going to be good for a real one. In some of them, it's terrifying, where they say, we have Koa, we download SimGrid, we implement a simulator, off we go. And they get results that doesn't match Koa. It matches something, but not Koa. So already, only 29 have both simulation and real-world results we can compare. And if you show that to a physicist, they freak out, and our entire field loses all respect, because you have a simulator, emission a curve, and you don't have any range of it for which you also have experimental data to show it matches. I mean, that seems horrendous, and yet that's what it is. 4 papers amazingly show real-world and simulated results, and they say, yeah, we don't care, no comparison. So that is very weird. Section 2 showed the plot, section 3 showed the bar graph, and here we go. In 15 of them, people say, oh, of course, we calibrated our simulator. So they show the simulator matches the real world pretty well. And they have a sentence that says, we tuned the parameters, we calibrated the parameters, we made it fit. And that I'm assuming, based on what I don't know, that the grad student wasted 6 months of their life picking parameter values until it fits. 10 papers out of 114 do what should be done, which is, okay, we have a simulator. Now we have ground truth data, and let's make sure that we document the procedure by which we make the simulator fit. And the procedure documented in almost all of those is purely manual. So it is a graduate student spending 6 horrible months trying to make it fit. All of those papers but 2, do I have it here? All of those papers but 2 are paper written by people like me, meaning the research result is the simulation method or simulation model. So of course I calibrate because my paper, if I say my simulation is not good, cannot possibly get published. So out of 114 papers, only 2 people behave the way I think all physicists behave. Meaning I have ground truth data, the experiments are too impossible. So I have a issue. I build a simulator, now it's bogus, but now I've got the real data, I make it fit, and now I'm confident in the simulator, and now I use the simulator for research. Based on that sample, it's less than 2% of users in this field doing this, which is super scary, but okay. So not okay, but so what can we do? So what we've been doing is saying, well, okay, if people don't calibrate their simulators, or if they spend 6 months doing it, we need to define the calibration problem formally, and it's not a very difficult formulation. We need to define what to optimize, how to pick the parameters that should be calibrated and the ones for which it's okay to be default. How do we pick the ranges, and how do we pick the optimization algorithms to use? In the end, it's only an optimization framework where you have to optimize to minimize the discrepancy between real-world results and simulated results. We implemented a framework in Python called Symcal for making this methodology usable by others. And we've been evaluating Symcal and using it for our research papers by, I'm not going to say wasting, but by exploiting tons and tons and tons of CPU cycles that POAD IPS has provided. Because this is super compute intensive now. It's a difficult optimization problem. And the objective function involves invoking the simulator many times. And the simulator can run in 10 seconds. And we run some algorithms like Bayesian optimization on this. So we may be invoking the simulator 20 million times. And so that takes 48 hours in POA. Right? So right now, as we speak, POA is running probably 96 jobs that each take 48 hours to calibrate yet another simulator. Once we have done that, we can compare an automatically calibrated simulator to a simulator that the user thought they had calibrated by hand, for instance. So we've done all kinds of case studies with different domains. There is one. So we were contacted by researchers at CERN in Geneva, and they want to simulate their compute infrastructure and for future executions. The particle accelerators there are generating more data every year, and what they plan to get of data in the next 5 years is enormous, and their current clusters won't cut it. And so now they have to say to the funding agencies over there, we want to buy that kind of cluster. But what about that kind? What about this other kind? And of course, you can't buy all 3, see which one works, and throw out the other 2, so you have to simulate. So they came to us years ago saying, we want to use your simulation frameworks to simulate our stuff so that we can try to make an informed decision about what we're going to build in the future. So they implemented a simulator themselves with our help. And then we never heard back from them, and they were running it, and they did stuff. And then they attempted to calibrate its parameters. So the simulator has parameters, and I'm not going to tell you what they are. There are about 12 of them that are very important. And they told us, here is our simulator. Here is the accuracy we achieve with respect to some ground truth data. And so there are 4 scenarios. It doesn't really matter what they are: slow cache, slow network, fast network. So there are 4 things we care about. But the important thing here, there are 2 rows in the table, and they all show simulation error. The lower is better. Like 1% means 1% error with respect to the reality. And so they're by hand calibration by a human expert who spent 6 months. That's why I've been saying 6 months, because that researcher spent 6 months. So I'm assuming any person would spend maybe even more. Got those errors. For 2 of the scenarios, around 20%, and for the other 2, 200% completely off. And you'll be thinking, what that guy is saying, when he saw it was 200% off, didn't he try to fix it? And the answer is, it was so labor intensive to do this that he cut corners for those scenarios. It was the fast cache scenario, and said, oh, for sure, the same parameter values and the previous scenario can be used only to explore 3 of them, not all 12, because, well, the 12-dimensional parameter space is and it's not huge, but it's not small. And so he basically gave up and said, you know what, forget it, that's the best we can do. I can't waste another year of my life. The guy is a physicist trying to deal with high energy physics. He's not supposed to be spending his entire workday calibrating simulators. When he goes back to his division director, what have you done this week? He cannot be saying, oh, this week I just tweak parameters for that random simulator, and it's still terrible, and I'll tell you that for another 6 months. So it's just not practical. And so we did something very simple. We said, okay, but before we had the SimCal framework, and we tried random algorithms for optimizing. So the stupidest one, in the 12-dimensional parameter space, pick a random thing, try it, okay? Pick another random one, try it. Oh, it's better, keep that one, keep going. For 48 hours, 1 core. So brain dead, but both. And even that stupidity got us a little bit better than human for the ones where the humans spent 6 months. And ironically, crazy good, 1 and 4% for the one the human kind of had given up on. Turns out with the fast caches, it's easier to calibrate if you think about it. So in fact, if that user had tried to calibrate the fast cache scenarios first, and then had maybe been kind of half-assed about the slow cache, maybe he would have gotten good results, but it was easier. But already we can see this is a dedicated, experienced human researcher, and by doing a random search for 48 hours in Koa, we just did so much better. And so the idea is to say in the community, yeah, no one wants to calibrate, it's horrible, but as opposed to publishing papers where you don't calibrate, how about you run for 48 hours on a cluster and then it's automatically calibrated. Now the challenge is a challenge, so that kind of solved it in a way. And now we have better algorithms than random search, of course, including Bayesian optimization, for instance. Now, the challenge in general is to understand where simulation accuracies come from. And that's very hard. Okay? So that simulation error there, 20%, why 20%? Are we fully simulating the network? This is what? Perhaps the simulation's level of detail is not sufficient. So maybe we went too crazy and abstracted too many things away. Right? So we cannot do this super fine detailed one that takes a million years, but maybe we kind of cut too many corners. But perhaps the level of detail of the simulation is fine, but the parameter values are wrong. So this is a stage before our work, where when people said, my simulator has 20% error, there was no way to tell your simulator is just inherently not good enough. Or, well, it happens to be good enough, but you didn't pick the right parameters. And so it was never possible to really be other than intuitively trying stuff to decide whether the simulator is inherently sufficient or not. And so that challenge has been played the simulation community. How do you pick the level of details for your simulator? Too detailed, what's the problem? Well, then it's slow. Not sufficiently detailed, well, then it's inaccurate. So what's the sweet spot? And so now that we have an automated calibration technique, we can calibrate the simulator automatically, evaluate its inherent accuracy, because now we calibrate it so that it can be the best it can be. And so now okay, let's see how good you are. If you tell me 20%, that's the best you can do. And then we take another one, we do the same thing, and that one says 10%, and then we can say, finally, this simulator is inherently better than that one. And if it runs twice as long, maybe then we decide to use it or not. So that is really the motivation I personally have had all these years to get to that point. So here is one case study, of course, a lot of details here that we did in a paper that is going to be presented in 2 months at the Supercomputing Conference. So we took the notion of the field of workflow simulation. So we have a computational workflow, which is a set of tasks in a cloud graph with input-output files, and running on a cloud platform with virtual machine on the Chameleon Cloud and SF-supported test bed. Perfect. And people have written simulators of those kind of things forever. There are tons and tons of them. And people have made different choices about how detailed the simulation is. So here for this paper, we said, okay, well, let's ourselves take one of the simulators and implement it in 12 different ways. 12? 3 times 2 times 3, yes, 12. So for instance, you implement a simulator of that stuff, and you're like, what? How do we simulate the network? We could go crazy simulate. On the top left here in that thing, the box, the network is a single network link with one bandwidth and one latency. And that's clearly that is not what the cloud looks like. That is a complete abstraction of the network. But then it's fast to simulate. And maybe it's good enough, who knows? Or you can say, well, that's too simple. Let's go one step to the right. Well, the network is going to be individual network links from a master to a bunch of workers. That is also not what the cloud looks like, but now it's a little bit more fancy. On the right, we say, okay, well, it turns out the network topology is actually closer to that, where we have one network link out of the master node, and then a dedicated network link to all the workers. Now that's starting to resemble more for a real network, but we're still far from the real network topology. And the question is, which one should be simulated? And it's really unclear if you don't have an automated calibration scenario. For the storage system, storage only on the master node, storage on all nodes. The cluster in the cloud, we know that every node uses the storage, but maybe you can get by simulating a slower storage or faster one only on the head node. So trying to cut corners. At the bottom, the system. Do you submit jobs or tasks to the workers directly, or do you use some framework like HT Condor, if you've heard of HT Condor? HT Condor comes with tons of overhead. I don't know about now HT Condor, but the overhead level is kind of insane. In the code of HT Condor, at some point, there is a sleep 7, for instance. So every job takes, a 0-second job cannot take fewer than 7 seconds. Right? So you have, that's a parameter, what is the Condor overhead? So, and every row here, from left to right, we have different options for simulating different parts of the system. Going to the right, we go more fancy, and more fancy means typically more parameters. So we have 12 versions of that simulator now, and we can now say, okay, what if we calibrate each of those 12 to the best of its ability? Now we can finally say, if you simulate something like this, it's not useful to simulate that thing in detail, and maybe it's useful to simulate that other thing in full detail. And so these are the 12 simulators on the picture. The x-axis is relative error, so to the right is bad, to the left is good. And now we look at all 12 options. So the top part is, what if we don't simulate the HT Condor system that the real system uses, or what if we do simulate? And when I say what if we do simulate, that means we have to go through the form of implementing a simulation of HT Condor. But that's why people would say, forget HT Condor, whether we want to implement a simulator of that, it's probably good. And we see here, for instance, that for that system, if you do not simulate HT Condor and you try to cut that corner, you lose. The simulators in the top part are much worse in terms of accuracy than the one at the bottom part. So that answers one question. Now, if we look only at the bottom part, we look at storage, which is the blue is all nodes, the whatever that color is only storage on the submit node. And we see here that there is one place where blue is actually worse than the other color, whose name I can't, orange. Let's say orange. I don't know what that is. And that seems weird because having storage on all nodes is more detailed. But the problem is, with more detail, the calibration problem is harder, and then you don't find the optimal. So there's also an argument for going simple, because with simple, you have fewer parameters, and now you can really calibrate well. So it's this raw kind of hot place. If you have only one parameter, it's very easy to make that simulator the best it can be, but the best it can be is starting. If you have a simulator with 400 parameters, the best it can be is amazing, but you never get there. And so that's what we're seeing. And then for the network, we have three network topologies, shared means topology and both. And we find that if you simulate the orange, basically it doesn't matter, and you can get by with a C. And so basically this is saying, for the compute framework, we go fancy. For the network, we go simple. For the storage, go simple. End of story. That simulator is the one you should use. So we can finally answer the question, at what level of detail should we simulate things? So simulation has been used a lot in cyber infrastructure research. The state of the art of simulation calibration is super problematic because as far as I can tell, people don't do it. The only people who do it are people who publish about simulation, not that use simulation for their own sake. And when we did that study, we read for those papers, and at some point it got really just terrifying to see how much research there. I basically don't trust at all, and it was even sad because that research was generated using software I wrote, and I cannot despise it, but okay. I mean, I can take a step away. I'm kind of one step removed from that. But to, as opposed to saying everything is terrible, let's give up on this. Instead, we have developed an automated calibration technique that improves simulation accuracy for whatever simulator. And because it does that, then it makes it possible to compare fairly simulators and to pick the level of detail. Okay, I have no idea what time it is because I don't see the time. Maybe I went faster, but that's all I had to say.
All right. Do we have any questions from the audience?
Not seeing any questions from anyone in the room.
I'm going to ask AI question.
Yeah.
How does AI change the way people try to do this?
So the question is, how has AI changed the way people try to do this? So we use AI to calibrate the simulator, right? So we use Bayesian optimization formula, machine learning inspired. So you would think that with AI, more people would say, oh, now we can calibrate, but I don't know. Is it because before you didn't even try a random search that now you're going to wake up and try some fancy AI stuff? I don't know. So in that space, honestly, I'm a little bit cynical at this point. I feel like people really don't. It's fantastic work in the calibration, but the only positive answer here is that simulator calibration should be the same thing as hyperparameter tuning for AI systems, and everybody does hyperparameter tuning. So this is kind of the same thing, and so it's kind of. I think maybe if I give this talk sufficient number of times, people will say, "Oh, but after all, we do hyperparameter tuning for machine learning models. Why don't we do parameter tuning using whatever Bayesian optimization for our simulator?" So far, I don't see many changes, but there should be a radical change. This idea cannot be crazy subversive by now. One thing that I see is people trying to saying implementing simulators is too difficult. And so, of course, with LLMs, we generate it automatically based on the implementation of the simulator. And that, like everything else, has a few examples of incredible results and 98% of the death of science. So I don't know. So that's the same thing as generating anything. But I'm a little bit, I was really shocked by that. So the thing we should be doing, which is a lot of work, is look at the next 5 years and see whether we have the same summary conclusion about the state of the art. Because in our paper, of course, we say this is just like hyperparameter tuning. So why do people do it? I think people love the notion. I mean, simulation. I think there's also a psychological phenomenon where you do a real experiment for a year, you want to kill yourself, and then you download a stupid simulator like mine. A day later, you have a simulator that says that ran in 3.7 hours. It will run for real, and you get that result in 1 second. Reproducible every single time over and over. You're like, oh my God, simulation is great. And I think there's kind of a tendency of saying, oh, there's a paper that says SimGrid is accurate. I'm using SimGrid, therefore I'm accurate. And in 1 day, I get a paper published on the possibility of that. And that's a very commonplace line of thought that is simply dangerous. I think that happens a lot.
It happens in the networking community.
Yeah.
Yeah, all the time. Most of their papers are simulations and they don't have to verify it against.
Yeah, so in the networking community, you have NS3, right? I read NS3, and there is a very scary paper. So there's a very scary paper. So why do we have to calibrate our simulators? Because the simulation is very high level and you cannot just put in the hardware spec. For networking, the networking people say, oh, whatever, I know the latency dynamics of every bit, the spec of every router, and I have an implementation of the TCP stack. So I know everything. And there is a great paper that is, oh my God, if you take a real network testbed and you take your NS of it, you still have to calibrate the parameters, otherwise you're way off. And I don't understand why that paper wasn't more of a event in that community, but I don't know. So even if you have a low-level simulator that is crazy slow, you still have to calibrate it, and that's super shocking to me. In our case, I didn't look at that too much because we can't use the simulators anymore. I think there were some Cyberinfrastructure, so there are some simulators of MPI applications. There is one called Codes, which is a follow-up to Ross by, I forget his name, I forget everything. The name is Ross and Codes, and they use NS3 for network simulation. And then their simulator is slower than real life, but then they write the simulator as a parallel MPI application that they run on a huge cluster. So to simulate a medium-sized cluster, you need to run the simulator on an enormous cluster. And then they use NS3, and then they say, because it's NS3, the network is 100% accuracy. So they do exactly that. Which I understand. I mean, calibration is just, Yeah.
All right. Well, how about we all thank Dr. Casanova for his very interesting talk.
Thank you.